Okay, so let's work on example 3.10 from the OpenStax textbook. Let's first read the problem. On dry concrete, a car can decelerate at a rate of 7 meters per second squared, whereas on wet concrete it can decelerate at only 5 meters per second squared. Find the distances necessary to stop a car moving at 30 meters per second on dry concrete and on wet concrete. Then repeat both calculations and find the displacement from the point where the driver sees a traffic light turn red, taking into account his reaction time of 0.500 seconds to get his foot on the brake. Okay, so that's a lot. This problem has many parts, so let's break it up into separate parts. So part A and part B is just asking from when you put your foot on the brake and you decelerate at a certain rate, how far do you travel before you come to a stop? So part A and part B have nothing to do with human reaction time or anything like this. In part C, we'll try to bring in that extra human reaction time part of the puzzle and solve at that point. So okay, the first thing we want to do is draw a picture, create a coordinate system, and write down our knowns and unknowns. Fortunately, they've drawn us a nice picture already. This is the type of picture that would be helpful for you to draw in solving any problem. So they've basically drawn for us an initial position of the car and x equals 0. They've given us this horizontal line to represent, the plus x axis, and they've labeled what is our situation at time equals 0. At time equals 0, and when we're at x equals 0, we have some initial velocity equal to 30 meters per second, and so they've labeled that here with proper notation. V sub 0, meaning your velocity at time equals 0, is equal to 30 meters per second. And they've even drawn us a nice velocity vector in green there to represent that we're moving pretty quickly in the plus x direction at that moment. All right. They have also labeled for us the final velocity equal to 0 meters per second, and they've drawn a little dot there to represent a velocity vector of 0. Right. So I want to point out that that's not given to you explicitly in the problem, but they are asking us in the problem how far is it going to be for us to bring this car to a stop. So we have to kind of say, okay, from this word problem I can recognize that my final velocity is going to be 0 because the car is coming to a stop. Okay. They also give us two other knowns in the problem. They tell us on wet concrete that the deceleration rate is 7 meters per second squared. Right. So decelerate generally is a word that means getting slower. So if we're moving in the plus x direction and we're getting slower, that means we have negative acceleration. So we need to then write down that properly in our physics notation, that the acceleration on dry concrete is equal to negative 7 meters per second squared. And they also tell us that on wet concrete, the acceleration is only 5 meters per second squared. So we don't slow down as fast on wet concrete. And we can label that properly with a negative sign because we know that acceleration is a vector, and we've defined the plus x direction to be positive direction, and the change in velocity is in the minus direction here. This is negative acceleration. Okay, and so in part B and part C, they want us to identify what is the distances necessary to stop. Right? So what they're asking for, what is our unknown here? The unknown is our displacement. How far is it from where this car hits the brakes at position x equals 0 to where the stoplight is, where they come to a stop? Okay, so that's just setting up the problem, drawing our picture, setting up our coordinate system, writing down our knowns and unknowns. The next thing we have to do is identify which concept is relevant to solving this problem. Right? And they didn't explicitly say it in the problem, but we can see here by looking at these two numbers that we have constant acceleration. Right? The acceleration on dry concrete is equal to negative 7. It doesn't change with time, it's a constant. Same thing on wet concrete, it doesn't change with time, it's a constant. So if we have constant acceleration, that indicates to us that there's a whole toolkit of equations that we can use to solve this problem, namely what we call the kinematic equations or the constant acceleration equations. Right? And so we can look at our lecture notes or at our equation sheet and find those equations. If you recall, there's 4 of those equations which are relevant to you, and we now need to identify which of those 4 are going to be helpful to solving this problem. So okay, let's first solve part A, which is for dry concrete. Okay. So of those four constant acceleration equations, I want to find the equation that has one unknown and everything else known, and then I can solve for that one unknown. And so it turns out with this problem, the one that we can recognize is going to be useful to us is v squared is equal to v naught squared plus 2a delta x. Okay, we can see this is going to be useful because we know our final velocity is 0, we're coming to a stop. We know our initial velocity is 30 meters per second. We know our acceleration for dry concrete is -7, so we can solve for our displacement, delta x. So delta x is our unknown here. That's what we're solving for. So I can solve this algebraically. Delta x is equal to v squared minus v naught squared over 2a. I can then plug in, because I've written down all my knowns nicely with this picture. So I have my final velocity is 0 minus my initial velocity, which is 30 meters per second quantity squared, divided by 2 times my acceleration on dry concrete, which is -7.00 meters per second squared. Okay, and I plug in and I find that the displacement is 64.3 meters. And that's my answer to part A. Okay, so that wasn't so bad. For part B, we just have to do exactly the same thing, but this time for wet concrete. So in fact, we can pretty much use the same equation that we've already done. On wet concrete, we can use the same equation. Delta x is equal to v squared minus v naught squared all over 2a. The numerator is exactly the same, 0 minus 30 meters per second squared. Right, we're still going with the same initial speed, but our acceleration is slightly different on wet concrete. This is 2 times -5.00 meters per second squared. And so when I plug in the numbers here, I find, let's see, what do I find? I find that my displacement is 90.0 meters. Okay, so it takes me much further to stop on wet concrete. Right, so this is just like real life. And we'll talk about this more when we get to talk about forces and friction in future chapters. Okay, so that was part A and part B. Part C is going to take a little bit of interpretation. We want to repeat these calculations, but we want to find the displacement from the point where the driver sees a traffic light turn red, taking into account his reaction time of 0.5 seconds. Okay, so what does that mean? So that means for part C that it's going to take some amount of time before this driver even hits the brakes, right? 0.5 seconds. So what that means is that the car is going to travel some distance during that time. There's going to be some displacement just during that reaction time, right, where the driver is still driving at a constant 30 meters per second, right? So we can figure out how far the car travels during that 0.5 seconds driving at a constant velocity, and then we can figure out how far they're going to travel after that when they're slowing down with the acceleration we already know about, right? And in fact, we've already solved for that. So all we have to do to find the total displacement is figure out the displacement during the reaction time and add to that the displacement while they have the foot on the brake. Right? And we've already done that. We know that on dry concrete it's going to take 64.3 meters for them to slow down with their foot on the brake, and on wet concrete it's going to take 90 meters. So all we need to really find out here is how far do they travel during that reaction time when they're driving at a constant velocity equal to 30 meters per second. Okay, so if you're driving at 30 meters per second for half a second, you drive 15 meters, right? But we can write that down more explicitly using our constant acceleration equations. In this case, I think this equation is going to be relevant to you. X is equal to x naught plus v naught t plus 1/2 at squared. Right? But during this period, during the reaction, our acceleration is just equal to 0 because you haven't put your foot on the brake yet. So this term is just equal to 0. And x minus x naught, if I move x naught to the other side, I have x minus x naught, or just delta x, which is what we want to find here. And delta x reaction is just equal to v naught t, right? Just velocity times time. And so that becomes 30 meters per second times 0.5 seconds, right? That's how long it took us to hit the brake, and that gives us 15 meters. Okay, so our final answer to C is that on wet pavement, on dry pavement, delta x total dry is going to be 64.3 plus 15 meters, or 79.3 meters. So that's that. And for wet pavement, delta x, oops, let me fix that. Delta x, ooh, too much. Big eraser. Okay. There we go. So delta x total wet is going to be our reaction, which is 15, plus our brake distance, which was this 90, plus 90, and so that gives us 105 meters. Okay, barely fit it all on the page, but we got it all done. So okay, that's that problem.